So when atoms or molecules absorb energy, that energy is often released as light energy. And we see this in fireworks, in neon lights. Each element emits a characteristic color. So here we have a neon sign. And that orange color is from neon gas. It's a glass tube with neon gas in it, and when you zap it with enough electricity, it will glow very bright orange like that. Over here we have some element lamps. This is helium and hydrogen. That looks like hydrogen. Anyway, those are the three elements there. They emit light that has a particular color. If we take the light from one of those element lamps and pass it through a prism, instead of seeing a rainbow of colors, we see a series of lines, a pattern of lines that's unique to that kind of atom or element, and it's called an emission spectrum. It's almost like a fingerprint. Classical physics cannot explain this, but quantum mechanics can. So what happens is you have a lamp, like a hydrogen lamp, and you pass the light through a slit and through a prism, and instead of seeing a whole rainbow, you get a couple of lines of different colors. Now, these are going to fall in the same place on that as if you put white light through. The orange-red light would be over here. So this is helium, this is barium. If you put white light through, you're going to see something like this. We've got oxygen and neon. These are, never mind. Anyway, so why do we get individual lines instead of a continuous spectrum? That was a big question. We can also look at absorption. This is an emission spectrum for mercury, and this is an absorption spectrum. So here we see that the mercury is absorbing energy. We're shining light on it, and it's absorbing energy that corresponds to the same energies that it emitted when it was excited. We just see dark lines instead of bright lines. If we put elements in a flame, they will change the color of the flame and give off a characteristic color. This is sodium, potassium, lithium, and barium. And the reason the color of the flame is different is because that corresponds to the wavelengths of light that are emitted when that atom gets excited. So the hydrogen spectrum was observed. Let's just go back and look at it real quick. This one right here, up here. Come on. Right here. So there's a purple line and sort of a blue line and a kind of a reddish-orange line. They observed that, and it didn't matter how you did it, hydrogen always gave off lines with those frequencies, those wavelengths. So a guy named Johannes Rydberg, back in the 1800s, early 1900s, looked at a lot of these different atomic spectra, and he found that he could describe with an equation the wavelengths of the light. And the equation had inverse square of integers, and this is what he came up with. 1 over the wavelength equals a constant times 1 over m squared minus 1 over n squared. Really cool, but doesn't explain anything. He's just like, hey, I found a pattern. Great. Doesn't explain why you get these discrete lines, why atoms are stable. Doesn't even explain why the equation works. It just does. So that leads us to Rutherford's nuclear model of the atom. So the atom has a tiny dense center called the nucleus. pretty much all the mass of the atom is in that nucleus, and outside of that nucleus are some electrons. The nucleus is positively charged. We've got a balance of charge between the electrons outside the nucleus and the positive charges inside the nucleus. This should be reviewed. What we're going to talk about now is what are those electrons doing? So electrons are charged particles, and they're moving. And according to classical physics, moving charged particles give off energy. So if that's the case, then electrons should be constantly giving off energy, which means that at least some atoms should literally glow. And the electrons should lose energy, and losing energy, they should crash into the nucleus and the atom should collapse, but it doesn't. So the nuclear model of the atom is not explaining what structural changes occur when an atom gains or loses energy. So we have to go a little further. So Niels Bohr developed a model that explained how the structure changes when energy transitions occur. So in the Bohr model, the electrons are traveling around the nucleus in circular orbits, much like the planets go around the sun in the solar system. The orbits exist only at specific fixed distances from the nucleus, and the energy of each orbit is also fixed. Let's say it's quantized. So the amount of energy in the atom is related to the electron's position in the atom, which orbit it's in. When we say that something is quantized, we mean that it can only have particular values. We actually have a lot of things in our everyday lives that are quantized. Our monetary system is quantized. So there's a $1 bill, and there are $2 bills, and 5, and 10, and 20, and 50. Have you ever seen a $17 bill? No, because they don't exist. You can have $17, but you'd have to have like 3 5s and 2 1s or some other combination, right? There are fixed quantities, and you can't have something in between. In grade school, you can be in first grade or you can be in second grade. You can't be in between. You're going up the stairs. You can be on the first step or the second step. You can't be in between. Going up a ladder. You can't stand between the rungs, right? You're on one or the other. Those things are quantized. A ramp, instead of stairs, is not quantized. It's continuous. You could scooch up just a little higher on the ramp, or just a little higher, or just a little higher. You can't do that on stairs, where you have to be on one stair or the next. So a ramp is continuous, stairs are quantized. So the energy of electrons in the atom is quantized. They can only have specific amounts of energy. So here's Bohr's model. We've got the nucleus, and then we have these different orbits that the electron can be in. And normally in the hydrogen atom, the electron will be in the lowest energy orbit, but if you put some energy into the atom, it can move the electron up to a higher energy orbit. Those higher energy orbits are not stable, and so the electron will return to a lower state, and when it does so, it releases the energy that it had. The energy released corresponds to the difference in energy between these two orbits. So when the electron moves from the 5th orbit to the 2nd orbit, the difference in energy there corresponds to violet light, and we see violet light that's emitted. The electron moving from the 4th to the 2nd level gives off a blue-green band of color, and from the 3rd level to the 2nd level we see this red band of color with a wavelength of 657 nanometers. The colors, the wavelengths are always the same because the energy levels in the hydrogen atom are always the same. An electron can be promoted to a higher level, and then it can return to lower levels, but it can't be in between. So the energy that's given off is a photon of light, a piece of light. The distance between the orbits is related to the energy of the photon. What's really weird about this is, so if these are orbits in the Bohr model, the electron can go from the 5th orbit to the 2nd orbit, but when it does so, it does not travel through the ones in the middle. It's a quantum leap. It goes from one to the other without going in between. It's quantum mechanics. This model is nice because it's easier to understand than some of the other ones. Unfortunately, it's also not correct. So why do we even bother to tell you about it? It helps us to picture what's going on. We know it's not right, but it's like a baby version of what's actually happening. And so, when we talk to young children, we simplify things, right? Because they can't grasp the more complicated version. Does that mean it's what we're saying to them isn't useful at all? No, it's useful. It helps them to understand enough of what they need. So this is like baby talk for electrons. It helps us to picture, because we can picture the solar system. The solar system is like, okay, the nucleus is the sun, and planet Earth is an electron. And if we got a bunch of energy, we could move our orbit from the current one to one that's farther out, higher in energy. You're like, okay, now we're starting to use our imaginations. It's okay. But we can picture that, right? So that's the idea here. And when we have a transition from high energy to lower energy orbit, that energy has to go somewhere. And it's emitted as a photon of light. These 3 transitions happen to give photons that have wavelengths in the visible region. You can also have a transition from 5 to 4, from 5 to 3, from 5 to 1, or from 2 to 1, 3 to 1. All these other transitions are possible, but those do not correspond to visible light, so that they don't show up on our spectra. So the electron's never observed between states. It's always in one or the other. The energy of the photon emitted is the energy difference between those 2 states. We can calculate the energy of the states from the wavelengths of the lines. So Bohr model has a lot of historical importance and conceptual importance, but ultimately was replaced by quantum mechanics.